Welcome to a new episode in English. Today's guest is Professor David Mota, a cosmologist at the University of Oslo. Today we will dive into the theories that challenge Einstein, post-Einstein gravity, screening mechanisms, and the mysterious language of gravitational waves. And then there is Euclid, the new space telescope launched by the European Space Agency, designed to map the universe in 3 dimensions, look billions of years back in time, and perhaps solve the riddle of dark energy. Is dark energy just a name for our ignorance, or a force that drives the very expansion of the cosmos? Fasten your seatbelts. We are heading to the edge where physics meets mystery. Hello, David. Welcome to the show.
Thank you very much.
Today we're going to talk about the big things in life: black holes, gravity, the universe. Could you please introduce yourself to the audience?
Yes. Well, first of all, thanks a lot for the invitation. It's really a pleasure being here. So, my name is David Mota. I'm a professor in astronomy at the Institute of Theoretical Astrophysics, University of Oslo.
Cool.
I'm a cosmologist. So, my professional life is try to understand the properties of the universe. What is the universe made of? What was the beginning of the universe, and what's going to be the future of the universe? And as a cosmologist, I'm also interested to know what are the laws that rule the universe, in fact.
And we're probably going to come by Mr. Albert Einstein.
Yes, we'll talk about...
he made some rules.
Yes, it is.
But I think that maybe we will talk a lot about what has been happening after Albert Einstein, post-Einstein theories. And that is what I'm really looking forward to.
Yes, yeah. So this is a topic that I work, in fact, is my main center of research, is to test gravity theories beyond Einstein theory of general relativity.
Yeah.
And the motivation for that, for the people who don't know, is that we know that Einstein theory of general relativity breaks down in the center of black holes, which nowadays we know they exist, and also at the time of the so-called Big Bang. Also, the theory of general relativity is not valid at the time of the Big Bang. So we know from the theoretical point of view that there is something strange about the theory of Einstein general relativity. So there may be another more general theory of gravity, a theory to describe space and time. On top of that, that's on the theoretical point of view. But from the observational point of view, when uses Einstein theory of general relativity to explain some properties of galaxies or properties of the universe, we cannot explain them. We observe phenomena. I can give details a bit later. And just with the Einstein theory of gravity, together with the matter that we know the universe is made of, like electrons, protons, quarks, what we are made of, stars are made of, we cannot explain what we observe.
Okay.
And the only way to explain, if we say, no, Einstein is correct, that guy was really smart and what he did was really the ultimate theory of gravity. If we assume that, then it means there must be something else in the universe which is not what we are made of.
Yeah.
And that's something else. It's made of 2 parts. One is called dark matter, and the other is called dark energy.
Yeah.
And what is impressive is that these 2 unknown stuff that there is in the universe, they are not just like a little bit of something which is just exists in the universe, and most of the universe are stars or comets or whatever. No. They represent 95% of the total universe.
So we have only a little bit of an idea of 5%.
Precisely.
There are many Nobel Prizes in the way.
There are many Nobel Prizes in the way. That's a very good point to do that. And this dark matter, dark energy, they are really unknowns. And we have been looking for them with many different kinds of experiments, with particle physics experiments here on Earth, for instance, with the LHC, for instance, one of them in Geneva.
The Large Hadron Collider.
The Large Hadron Collider, for instance, with the other telescopes in the South Pole. looking at the universe, at how galaxies form, etc. And up to now, we have very little clues about what is dark matter and dark energy.
Yeah.
So, so I think I'll be employed for quite some time. I don't think I will solve the mysteries of the universe in the next decades. No, I don't think so.
Possibilities are really enormous, and I think it's so fun to have this kind of thoughts that you can experiment on and actually try to figure out what is all these unknown things.
Yes, yeah, precisely.
Yeah.
And so, yes, and I think the first step, if I can move forward and tell you something about it, like the first step when you try to understand something that you don't know is to try to look for it, try to extract properties of these unknowns. And for that, we need telescopes because telescope allow us to see the light that comes from the universe. And since 2015, we managed to detect for the first time gravitational waves.
Yeah.
And in fact, gravitational waves, it's another way of seeing things. In fact, it's more like hearing the universe.
So we get a new sense, actually.
It's a new sense, precisely. So gravitational waves, we can, it's basically waves, fluctuations in space and time. So space and time moves. Like if you can imagine that space and time is like the surface of a lake, water, and you throw a rock in the surface of the lake, so you'll create these waves. And these waves will propagate from the place where the rock fall into the water all the way to the shore.
Yeah.
And we can imagine ourselves, we being on Earth, are the astronomers at the shore of the lake and seeing the pattern of waves that come to us.
Yeah.
So you can imagine if I throw, I don't know, an airplane in the middle of the lake, I'm going to get huge waves with a very given pattern. If I throw just small pebbles in the middle of the wave, the pattern of the wave is going to be different. So depending on the pattern of the waves, it's a way of seeing what's out there.
Yeah. But Einstein, he actually predicted gravitation.
That's true.
Yeah.
And the gravitational waves.
Yeah.
That's true.
And how did we go about actually detecting them?
Very good. Yes, that's a very good question. So the way we detect them is that Einstein predicted gravitational waves and black holes, the existence of these compact objects, where they are so compact, there's so much mass, gravity is so strong that not even light can escape them. That's why they call it the black holes. And what Einstein also predicted is that when black holes, for instance, they spiral around each other and they merge, they will create a wave into space and time, just like the waves I mentioned about the water. So the way we detect it is because when a gravitational wave goes through to us, like in between us, and now our gravitational wave is going through us, the distance between you and me, it will increase and will decrease.
Yeah.
So in fact, I'm exaggerating here completely, of course. It will be like I seeing you close to me and far away from you.
In the set. Okay, so we will actually move.
We are moving now.
Yeah.
We are. Of course, we are moving a distance which is about 10 to the minus 22 meters.
Yeah.
So that's the size of a nuclei of an atom. So we don't notice with our eyes that you and I are in this moment fluctuating closer and further away. We are fluctuating. There's a wave, several waves going through now.
Yeah.
And it took, I think, 70 years for physicists to build instruments which could be sensitive enough to measure these small fluctuations in the distance between objects. So they created the first experiment was called the LIGO and the Virgo experiment. So these are two experiments in the United States where basically have two mirrors and there's a laser in between the mirrors. Just like you and me, we can be two mirrors and there's a laser between us. So it measures very accurately the distance. Now, when there's two black holes, for instance, merging in the universe, they will create a quite strong gravitational wave.
The plane in this lake.
Yes, in this lake, yes. It will propagate from, for instance, some part in our galaxy, to black holes in our galaxy. They merge, they propagate these gravitational waves, and will come to Earth.
Yeah.
And these mirrors with the laser, they will oscillate the distance between them.
How far away were they to actually measure this
So
oscillation?
the mirrors are about 100 kilometers from each other. Yes. They are buried on the ground.
Yeah.
And they need to be sensitive to this oscillation of about 10 to the minus 22 meters. So you can imagine just like, for instance, just driving through that area will create oscillations.
Yeah.
Just the fact that the laser heat ups the mirror, it will create,
Yeah.
the atoms of the mirror will move. So the physicists took 70 years to simulate all this, to be aware of all these kind of possible effects
Yeah.
that will mimic a gravitational wave. Yeah, so
Yeah.
that's why they got the Nobel Prize
Of course.
a few years ago, because it's an amazing piece of work. Well, it's thousands of people worked
Yeah.
on that from all. And the way they do, in fact, is like because a gravitational wave, it's really like hearing. It's not so much light, it's something that propagates even without a medium. The gravitational wave propagates in space and time like water. So what they do, you can imagine that they were looking for specific patterns on the wave. So let's imagine that, for instance, I'm Portuguese, people know. So I can speak Portuguese, but then suddenly I say a word in Norwegian.
Yeah.
So, bom dia, Joaquim, nós, podcast, whatever. So I said something that you didn't understand,
Yeah.
and then I said the word norsk, that you understood, so your ears captured that word.
Yeah.
It's the way they do it with gravitational waves. So they have like a template of what should be the amplitude, the frequency
Yeah.
of the wave, and they are always hearing, looking always at the mirrors. And when the mirrors move with that pattern, that's the gravitational wave.
Yeah. Can you actually then calculate where it came from and how old it is?
Yes, you can. So
Yeah.
precisely with the gravitational waves, you assume that the theory of general relativity is correct. That's an assumption. You do the calculations from the Einstein equations and you calculate the distance where the gravitational wave came from, the source. You can calculate what is the mass of the objects that merge into create a gravitational wave. That's why, for instance, we know that the first gravitational wave that we detected was two black holes with a mass of around 20 something, 27 and 26 solar masses that they merge together and they release, in terms of energy of gravitational waves, the equivalent to two suns. Two suns. So lots of energy.
Two suns for our galaxy.
Yes, from ours,
okay,
yes. And then they release this energy. So we can calculate what's the mass of the object, the distance, and how far away, how long they rotate around each other. So we can extract that information.
Yeah. And why is this important?
Yes, very good question. So this is important because up to 2015, the only way we had to search and observe the universe and search for this dark matter and dark energy and whatever is in there is through light. Like now you're looking at me. You can see, okay, there's a guy here, he's around 50 years old, he's bald, brown eyes, he has some beard. But if I don't speak, there's a lot of information, like you wouldn't know that I'm a cosmologist, that I work on gravity.
No.
Yes, because you can only see me. But now you can also switch off the lights in this room. Okay, you don't see me at all, but I can talk. So I can pass information to you just from my voice, even without light. So it's the same about the universe. At the universe, up to 2015, we could only see the universe. You can only see stars and galaxies, so objects which emitted light. So black holes, they don't emit light. There are many other objects which are very far away from us, like neutron stars and other objects. They also, the light they emit, if they are very far away, we can't see it.
No.
So, but with black holes, even if we don't see the object, we can still hear them nowadays.
Okay.
And that's when now
But only when they merge, right?
Yes, that's right. They
okay.
need to merge.
Yeah.
The black holes, the neutron stars, they need to merge. But when they merge, we can start seeing properties of our galaxy in there. So it's like, for me, it's like being in a forest. During the night, you can't see anything around you. But if you start hear the sounds of the animals, you know they are there.
Yeah, it's
Yes.
yeah.
So before we didn't know there was, for instance, so many black holes in our galaxy. We didn't know how many black holes. We could not even estimate how many black holes there were in the universe.
No.
And nowadays we can start doing these estimations
Yeah, that's
about
cool.
the number of black holes there are, how big the black holes are, how do they evolve, and all this brings information about our universe.
Yeah, and it's also it has to help also with the understanding of how the universe moves
That's right. So
because they are so massive.
Yes, and also, for instance, one of the biggest discovery in astronomy that we had was by Edwin Hubble. He was an astronomer who discovered
The telescope.
Yes,
Yes.
with the Hubble telescope. That's why he's named the telescope. And Edwin Hubble discovered that the universe is in fact expanding, so it's growing. And in 1998, a group of astronomers in the US and Australia that discovered that the universe not only was expanding, growing, but was also accelerating,
Yeah.
which is something very strange for a universe, because you can imagine that if I have a universe which is expanding, is growing, the universe is full of matter, stars
Yeah.
and galaxies and maybe the black holes. So they attract each other via gravity. So the expansion of the universe should be slow and slower and slower.
Yeah, because it will actually stop or gravitate together.
Precisely, yeah, they gravitate together. And so the expansion could even stop and just collapse again, our universe. And this is what we all were expecting for the universe to happen one day.
Yeah.
With the universe
Big
expansion
crunch.
to start, a big crunch. So the whole universe would collapse again.
Yeah.
And what they found out in 1998 is that our universe was, in fact, the expansion of the universe was accelerating. So there must be something in the universe which is anti-gravitates. Yes, this anti-gravity thing. And this thing, we look at the universe, but we can't see anything.
No.
We only see stars. So what's that thing that's making the universe to expand in an accelerated way?
Yeah.
That thing that we can't see, but seems to be there, it's called dark energy. That's what we call dark energy.
Is it dark energy because we don't actually know what it is?
Yes, precisely. It's just
so
a
it's-
way of giving a name to our
Yeah.
ignorance. It's dark because we can't see. We have been looking around. And then this energy which makes the universe accelerate in this kind of anti-gravity kind of behavior.
Yeah.
Now, just to go back to your question, because your question was what is it important and how this is linked to the expansion of the universe, is that the way they discover the dark energy and the expansion of the universe, Hubble, and then later in 1998, was looking at the light of very far away galaxies. And what they see is that these galaxies were dimmer and dimmer the further away they were. So that means, galaxies and then supernovae as well. Supernovas are just stars that explode.
Yeah.
And they saw that with this luminosity was so dim, it means the universe was much bigger than we expected. So it means the universe is expanding. Now, light is something that gets dimmer very quickly. For instance, if I have, a light source, one of these lamps, and I took very far away to Carlyon or to the opera, maybe you won't be able to see this light anymore, because the intensity of light, the number of the photons, the light particles that are emitted, they just get scattered in the universe. You won't be able to see it. It's just a very far away light. So you imagine the universe is so big that there's a lot of stars and galaxies and objects in the universe that we can't see. Not because they don't emit light, it's because they're just far away.
Yeah.
So with the black holes merging, when black holes merge, they can be very, very far away, much further away than these light sources, but we can still hear them because gravitational waves, they get dumped in a very light way. So they can propagate much, much further away than that. So we can use black holes merging and making these bangs in terms of noise from objects which are much further away. So we can see the universe, or you can hear the universe at much
Farther away than
further
we can see them.
Then we can see them, precisely. So it's strange because sound, we have the feeling that
It's slower.
it's slower, yes, and we can only hear sounds very close by to us. And light we can really see far away. And gravitational waves is the opposite. We can see gravitational waves much further away than we can see light.
Okay.
So it's a very fantastic way even to go to the past, because remember, the further away you see, you are going backwards in time.
Yeah, it's this also this famous thought experiments. If you put a mirror in the space, you can see back in time.
Yes.
If you have it far enough out, you can actually see back in time.
Yes, that's right.
Well, now that we know that gravitational waves are real, we can detect them and we can also measure them.
Yes.
How do we come about actually measuring how many black holes we have in the galaxy or in the universe?
Oh, that's a very, it's a difficult question. So I can say that we estimate the number of black holes from, it's kind of a statistical way. So let's put it like that. If there are many black holes in the universe, if the black hole is the universe is full of black holes, the density of black holes is very high, it means the probability that they merge is very high. So we will listen a lot of these waves. We will see lots of gravitational wave signals. If there are only like a few black holes in the universe, then the amount of gravitational waves that we'll get is going to be very low. So by the amount of gravitational wave signals we receive, we can estimate, doing some statistical analysis and take into account some properties of the universe, the number of stars there are in the universe, for instance, how many black holes there can exist. Because black holes, they are mainly, the main source to create black holes is from stars. Very big stars, which stop the thermonuclear reaction, so they don't emit light anymore. They collapse and they form a black hole, or a neutron star, which is another way of compact objects. So if you count the number of stars in the universe, you can estimate, okay, a star, very massive one, lives for a few million years or few billion years, and it means it will be converted into a black hole. So you can do these kind of estimations. And then, so you count the stars, you know how long they live, you estimate the number of black holes, and then you can somehow confirm that with the amount of gravitational waves that you can hear. And that gives you an estimation of the number of black holes. So in our galaxy, if I'm not wrong, probably I am, I think we have several millions of black holes in our galaxy, just in our galaxy.
In the Milky Way.
In the Milky Way. Millions of black holes.
Yeah, okay.
So there's a lot of black holes
They are common.
Yes, they are quite common. Yes.
Do you think if we follow the projections that we will have more black holes than stars? Or is it being created stars also, or is it just creating black holes?
That's a very good question. No, there are some stars that are also being created. There's still some gas in the universe which will collapse and create stars. And many of the stars, they don't end up in black holes. So stars with less mass, they will just explode, for instance, in supernovae, and this gas will be spread in the galaxies and will collapse again, will create new stars. But there are many stars that they will die out. And they will die in a graveyard of black holes. So all these black holes that we have in our galaxy, they're probably coming from stars that just died. So it's our local graveyard, let's say, of black holes.
I think one of the exciting things that I think about black holes is the white holes, where they explode. Where is all the energy going?
Yes, that's a good question. And I don't know, and I think nobody knows. So white holes are a mathematical prediction of general relativity, and people manage to create some kind of tunnels, wormholes between black holes and white holes. But I think at this stage it's just a mathematical solution, an artifact. So nobody has ever seen or detected any signatures of the existence of white holes. But maybe they exist. I don't know. But we don't know.
Let's see.
Let's wait.
Okay. But we were talking about some of the things in the general relativity that is wrong. And where are we now in the state of expanding our current knowledge about the general relativity post Einstein.
Yes. So when I mean so I'm not sure if the word wrong is the correct one. Is that general relativity cannot explain, we cannot have a good understanding of what is space and time, for instance, at the time of the Big Bang.
No.
Because time and space become somehow one. At the time of Big Bang is that time stops existing, even the whole universe as a space stops existing. So it's a singularity, that's what we call. So it's something that we cannot mathematically have a good description, nor physically as well.
Yeah.
So there must be something else besides general relativity that we believe, and we've also, because there are two main classes of theories on physics. One is the classical theory of physics, which is general relativity, that describes space and time. And then you have the quantum theory of physics, which will describe the particles.
Yeah.
And both of them are fantastic. So when we do tests for general relativity, when we send satellites in the solar system, we try to see if they follow the signals they send to us, if they follow general relativity. They do perfectly. When we see the mergers of black holes, gravitational wave signatures, they are just exactly what general relativity predicted. So there's no indication that general relativity is wrong from the experimental point of view. But if we say there was a Big Bang,
Yeah.
then general relativity cannot explain the Big Bang. Maybe there was no Big Bang. Okay. Well, I don't mean, when I say maybe there was no Big Bang, the universe at some point was very small and very hot. But it doesn't mean there was a singularity.
No, it was just compact, maybe.
Yes, just compact. But even inside the black holes, general relativity breaks down. So we have all these theoretical issues that mathematically they don't make sense. So if we believe in quantum mechanics and we say, no, this quantum mechanics is really a correct theory to describe quarks and electrons and light and neutrinos of the particles, then we should be able maybe to unify them, to create this unified theory of everything.
Isn't that a quest?
It's a quest. It is a quest, yes. And some people really believe that theory is there and we should try to find it. Other people say, no, we should not try to unify general relativity because space and time should not be on the same nature as electrons or quarks, because space and time is something and electrons and quarks are the thing. But what is important here, it doesn't matter the belief of the physicist, because science is not a democracy and it's not about belief.
No.
It's not about that. So we just need to find out what is the correct one. So motivated by those theoretical issues and the fact that we don't know what is dark matter and dark energy, people start thinking about maybe we can explain phenomena in the universe, like for instance, the acceleration of the universe without this dark energy component being there. Or we can also explain properties of galaxies without the dark matter component, which is there as well. And by just changing general relativity.
Yeah.
Okay? Because for instance, let me give you an example why we believe there is dark matter. So one of the examples why we believe there is dark matter is because we can see a phenomenon of the bending of light due to massive objects. So this was one of the first proofs that Einstein theory of general relativity was correct. Basically, you can see, you look at an object, you look at the galaxy, and sometimes you see the same galaxies twice. Yes? Or sometimes in 3 or 4 points in space.
Okay.
So that means, but when you look at the galaxy, we don't see anything between us and that galaxy that we'd see several images. So it means there's something dark in between us and that galaxy that created this space-time curvature, which makes the light bend, the light rays bend. But that's because we're assuming general relativity. For general relativity, in order for space-time to bend, we need to put something there.
Yeah.
We need to put a star or a black hole or a galaxy there. But maybe general relativity is not the correct theory of gravity, and maybe we can have space-times which bend without the existence of matter there. Yeah, so we don't know. And as scientists, you need to go after all the possibilities. So people start to think, okay, let's take a look at gravity theories which go beyond general relativity and can maybe explain this phenomena that I mentioned, lensing phenomena, gravitational lensing, or other phenomena, without the existence, for instance, of dark matter and dark energy. So one way that people thought was the following. If we look at the strong interaction in quantum field theory, which is the interaction responsible for quarks coming together to form protons and neutrons, we have 8 carriers of the strong interaction. So because quantum mechanics is about, if there is a force, it means there's a carrier. A particle carries this force. Yeah, so for instance,
The force or energy?
what we call the force.
Okay.
The particle carries energy,
Yeah.
but for instance, the electromagnetic force, we have a carrier, which we call the photon. That's light,
Okay.
basically.
Yeah.
Yes? For the strong interaction, for 2 quarks to come together, or 3 quarks to come together to form a proton is made of quarks, we need the so-called gluons, which are the carriers of the strong interaction. And there are 8 gluons. So for one interaction, there are 8. For the electromagnetic interaction, there's only one carrier, is the photon.
Okay.
For the weak force, is the other interaction in nature, there are 3 carriers.
Okay.
Okay? For Einstein theory of general relativity, there's also one carrier, which is space-time, let's call it, or some people call it the graviton. Yes? But if you think, well, for the strong interaction, we have 8 carriers. For the weak interaction, we have 3. It's true that electromagnetism, we only have 1 carrier, and gravity 1 carrier, but maybe there are some other carriers of the gravity interaction that we don't see.
Yeah.
So this is one way of expanding general relativity, going beyond Einstein general relativity.
Yeah, so not saying wrong, just elaborating.
Elaborating more. So for Einstein, there was only 1 carrier of the gravity interaction, the graviton, and maybe other people say, no, there's not only one, but maybe there are other ways that gravity propagates besides this graviton particle. And they can add either 1 particle more, 2 particles more. That's one possibility as well.
Yeah.
And gravitational waves, the event of the gravitational waves, in fact, was a gravitational wave phenomenon in 2017, ruled out a whole group of theories of gravity beyond Einstein.
Okay.
So there was a group of theories of gravity that was saying Einstein general relativity is not correct. And many people worked on that. There were dozens of scientists working on that. They really believe, oh, we are into something new.
Yeah.
And gravitational waves said that's not correct. And I can give you just an example. So this series of gravity are called massive gravity.
Okay.
Yeah, so Einstein theory of gravity is massless, there's no mass. So the particle that transmits the gravity interaction, you and I, we feel attracted by gravity because we exchange gravitons.
Yeah.
For Einstein, this particle, the graviton, is massless, has no mass.
Okay.
And that means it travels at the speed of light, just like the photon has no mass. Just to give an example, the particles that carry the weak interaction, which is responsible for radioactive decays, the nuclear decays, they have a very big mass.
Okay.
So they travel very slowly, much less than the speed of light. Okay. So there was this group of people that created this theory called massive gravity, very similar to Einstein gravity, but the only difference is that the graviton had a mass.
Yeah.
And this theory was fantastic because you could explain the acceleration of the universe without a dark energy.
So they thought they actually had a new thing for dark energy.
Precisely.
Okay.
And they said, now we can explain the universe, it's accelerating without putting this dark energy, which nobody has saw it. Just make the graviton, this gravity particle, give him a little bit mass. And this was very nice. Everybody was very happy about that theory. Myself as well. I worked on that. Everybody was really excited, up to 2017. In 2017, something happened in the universe, which was a black hole was inspiraling a neutron star, in fact, a pulsar, which basically is a neutron star that emits light every fraction of a second. And when they merge, the black hole and the neutron stars, they create the gravitational wave. So with these detectors in the US, we measure the gravitational waves. We know the distance to this system, and we measure how fast this gravitational wave traveled. But the pulsar, it also emits light.
So you could double check it.
We can double check it precisely. So when they merged, we saw this explosion with light, and light also traveled all the way to the Earth. And we saw that the gravitational wave traveled very close to the speed of light.
Okay.
So up to 10 to the minus 22. The difference between the speed of light and the speed of the gravitational wave is 10 to the minus 22.
Okay, so it's very close.
It's very, very close.
Yeah.
So it means that the graviton, having a massive graviton, it's not a good option.
No.
Because if you are very heavy, you just run slow. That's basically the law. Yes.
Are you saying that fat people can't run fast? Or
Maybe.
I'm just joking,
Yes.
of course.
But
I'm
the
just
massive
joking.
gravity for sure would run much slower
Yeah.
than the light. So what would have happened?
Are we sure about that?
We are quite sure about that, because otherwise we would have seen the light coming,
Yeah.
and after maybe a fraction of a second we would see the gravitational wave coming, and we saw them coming at the same time.
Okay. Yeah. So then the speed is plus minus the same.
Yes, it's very close to the same. It doesn't mean there are not other theories beyond Einstein general relativity. There are, and still valid. But one thing that we learned in 2017 is that at least gravitational waves, they should travel at speed of light. So if you come up with the theory which you believe is better than Einstein, if you think you are better than Einstein, at least make sure that gravitational waves travel at the speed of light.
Yeah. Yeah, because that we can check.
We can
or
check
we
that,
have checked and we can.
Yes, unfortunately, we only checked with one phenomena because this only happened once.
Yeah. But
So we are looking now for other
of course, yeah.
mergers. Yes.
And with the new telescopes that we have, it would be possible to see more, so that we can look for it when it's happening with the mergers. Yeah.
Yeah, that's a very good point. So now what we are doing now is that telescopes, which are instruments that will detect light, are now always on alert when the LIGO, Virgo, Praga gravitational waves experiments detect gravitational waves. And they are always on alert. So if there's a gravitational wave coming and they believe it comes from a system with pulsars or neutron stars, so we will see light, then the telescopes will turn quickly
To that place.
to that place to measure how light comes, because it's a way of but it's not an easy task. It's
No,
not an easy task. Yeah.
The universe is big.
The universe is big,
And
and they're
it's,
coming from all over the place.
It's more than you can't say it's 360 degrees either, because it's more.
In terms of directions.
Yeah.
Yeah, it comes 360 degrees. That's correct. Yes, so it comes from all directions.
So
in
you
the
will
sky.
actually call it 360 degrees, even though it's not just around the circumference, or
Yes, we don't know. You mean what's the geometry of the universe? It's true that we. Good question. Yes, that's very good. So it's true that the geometry of the universe, in fact, we believe it's quite flat, but it's a three-dimensionally flat.
Okay,
So let's call it like that. Yes.
it's not flat land.
No, it's not flat line. No. The Earth is not flat for sure. That I'm sure.
Sure.
It's the only thing maybe I'm
Groundbreaking
sure.
news.
Yes.
Are you willing to stand by that comment?
Yes, on that one, yes, I am.
Yeah, okay.
But
I will not challenge you.
no, I can. Yeah. And in fact, it's one of the few things, because as I told you some time ago, I hope that when in 1,000 years there's someone doing a podcast with someone else, with another scientist, I'm sure that they will be talking about concepts that we are not talking here. I'm sure science will be such a big revolution. Maybe the concept that we talk about, space and what we call time,
Yeah.
I believe even that concept of what is time and what is space, they will be talking about something else. That's the only thing I'm sure, and that the Earth is not.
No, I think time is probably one of the things that we do not understand, and that I feel like some people live wrong about time also, that they follow the clock, not the time, because as you know, the time travels different, and sometimes we follow the clock no matter which direction we actually move.
That's right.
Yeah, so I think sometimes you should stop looking at the watch and just living by the pace of your life.
Yeah, absolutely.
But what is time?
That's a really good question. And I think if someone, yes, to be honest, I don't know. It's a really strange concept. What is time?
Because the clock is just a measurement.
The clock is just a measurement. That's true. You just measure the clicks, the ticks that happen with a given frequency.
Mechanically.
Yes. But we don't know what is time, and it's very difficult when you write down the equations in physics. Timing going forward or backwards, it doesn't make any difference in the equations. The only area of physics where maybe there is an explanation for the arrow of time is in thermodynamics.
Yeah.
That second law of thermodynamics, which says entropy should always grow.
Yeah.
And some people associate entropy to time, but it doesn't mean it's the same thing. So
yeah, I think this is really strange. I read Stephen Hawking's book Brief History of Time, and I was just confused afterwards.
Yes, no, nobody knows what time is.
Yeah.
And but many people work on that. Some people propose that time is another particle.
Okay.
Just like
the time particle.
Time is a particle which travels in a very specific direction, and that's why we perceive time as going in a given direction. So you can see how crazy it can be. That, but these are serious scientific methods.
Yeah.
That time can be another field, another particle, and there's even a clock particle, let's call it.
Yeah.
That makes time flows somehow. What we call time.
Yeah. Because I mean, we use the clock a lot in your equations, so it's actually it would be useful to know exactly what it is.
Yes, absolutely.
It would be one of the 95%. It would be nice to know what time is.
Precisely.
Yeah.
Precisely.
Okay.
Yes. No, it's a very important concept. Yes.
Yeah. Dark energy. What would you, if you were to try to explain it to me in a really easy way? How would you say it?
So dark energy is really the two words that we give to something that we need to put into the Einstein equations in order to explain why our universe is accelerating. So what the Einstein equations say is that the geometry of the universe and the dynamics of the universe, in particular of the space and time, depends on what exists and what lives on your space-time. And what the Einstein equation says that if what lives in space and time is just matter like we are made of, we, the screens, the stars, the galaxies, the black holes, if that's what exists in the universe, then my space-time can expand, which is a strange phenomenon, but okay, but it can expand, but at some point we'll just stop the expansion, collapse, or will expand up to stop. Yes, and that's an exact solution of the Einstein equations. So dark energy comes because in 1998, this group of astronomers in the US and in Australia, they discovered that space-time is stretching, growing, and it's accelerating. So that means, from the Einstein equations, that means there must be something else in the universe which is not the type of matter that we are made of. Something else which makes our space to stretch even faster. And this is what we call the dark energy. The main candidate for dark energy that people came up straight away, and I think even in the same year that they made the discovery, was that is the so-called cosmological constant.
Yeah. Can you explain the cosmological constant?
Yes, let me try. So from a historical perspective, in fact, the cosmological constant was something that Einstein, he's the one. So it's difficult to be smarter than him.
The goat.
Yes, the goat, precisely. So that Einstein, when he wrote down his equations, the Einstein equations, there were some people, in particular, a bishop, a Belgian bishop, and a Russian physicist. They solved the Einstein equations for the universe and told Einstein, your universe cannot be static. It must be always growing or collapsing. So that's very strange because you cannot form structures in the universe if it is always growing, or we have already been on a black hole.
Yeah.
So it's very strange. So Einstein didn't like that possibility that his universe was always growing or collapsing. So he introduced it as a constant. It's really a constant into his equations, which balances out the universe. So it doesn't let the universe nor to grow nor to collapse.
Okay.
He introduced this cosmological constant. But then Hubble came, and Hubble said, no, the universe is not static, it's really growing, so let's forget your cosmological constant. And the cosmological constant disappeared.
Yeah.
In 1998, they discovered the universe was accelerating, and they discovered if they put a constant into the Einstein equations, with the sign inverted, with an inverted sign from Einstein, that this cosmological constant, this constant could create a universe which expands in an accelerated way.
Okay.
So when you do science, you say, okay, I put a constant in my equations and I explain what I see. It's not very good science, yes, because
It's
you
like,
say, yeah, you are.
is it like the equivalent of having duct tape in your project?
Precisely. It's like duct tape. In
It
the
holds it
project.
together, and now it's working.
Yeah, now it's working. We have no idea where the constant comes from. It's just duct taping. And then that's precisely the point. So people wasn't very happy about that. But then people who work in high energy physics, in particle physics, they say, wait, guys, because in quantum mechanics, in high energy physics, the vacuum, so the emptiness of space, there is energy there. In fact, that's the whole idea of quantum fields, is that in the vacuum, there is energy, and this energy produces particles, produces electrons, photons, neutrinos, produces particles. So there is energy in the vacuum. So when you are in empty space in the universe, you think there's nothing there, but there is energy, and this energy makes space to expand, to accelerate. So they say, wow, so maybe the cosmological constant is in fact that quantum energy of the vacuum.
Yeah.
So people were all excited and say, wow, we found it. So we found the universe accelerating, and we found the reason for that is because quantum mechanics is the correct theory to describe the particles. We have energy in the vacuum, the emptiness, in fact, there is energy. And this energy is making our universe to grow in an accelerated way. So everybody was very excited up to the point, okay, so let's calculate how much of this vacuum energy is predicted for us to explain the existence of electrons and neutrinos and quarks. Because, okay, there's energy in the vacuum, but we don't see things popping up in front of our eyes, yes? So they should exist, but they should pop up at a given level. So they went to calculate how much energy the particle physicists and the cosmologists as well, who predicted the expansion of the universe, say, okay, let me see how much dark energy do I need to put in there in this cosmological constant to make the universe accelerate. And for the cosmologist, the number was really, really tiny.
Yeah.
Really, really tiny. Really, it's 10 to the minus 3 electron volts. So it's a really, really tiny thing. It's almost less than the energy of a neutrino, which is almost a massless particle.
Yeah.
So just a little bit, it's really strange, but just a little bit, boom, the universe starts to accelerate.
Yeah. Is that because it's so much?
Yes, because the universe is so big,
Yeah.
so you just put a little bit and then it's enough to make it accelerate. And then they went to the high energy physicists, to the particle physicists, to the physics department, our colleagues, and ask, okay, what about you guys? How much do you get? Do you get also a small number? And they say, no, we get a huge number.
Is this the 0 point energy?
Yes, it's a 0 point energy.
Yeah.
Yes, the vacuum energy is 0. And they say that we get a huge number. And the difference between the numbers is 10 to the 60 orders of magnitude. So the number is a 60 zeros difference between what the cosmologists need and what the particle physicists need. In fact, yes, it's such a big discrepancy that nowadays people think, okay, yeah, the cosmological constant is a very easy solution, but it's really duct tape only.
Yeah.
So we have been looking for, okay, so if it's not a cosmological constant, so what it is?
Yeah.
And then here I'm involved in an institute in Norway. We're involved in a satellite called Euclid.
Okay.
This is a satellite by the European Space Agency whose main mission is to try to discover as one main single property of this dark energy, which is how does this dark energy evolves in time.
Okay.
Because if it is a cosmological constant, it does not evolve. It's always a constant. From the Big Bang to nowadays, the dark energy, cosmological constant, is just the same.
Yeah.
But maybe if dark energy is something else, is a new particle, for instance, a new field, then it should evolve in time.
Yeah.
But if it evolves, we should see it in the universe, for instance, how galaxies form. And this satellite is a €1 billion satellite paid by all of you. Thank you for your taxpayer money. Thank you.
So happy to do it. Yeah.
Yes. And it's now flying.
Yeah.
And the first data will come next year, next spring.
No.
Yes.
Sure?
Yes, yes, yes.
Okay.
So
That will be really interesting.
it's going to be fantastic because we might come with at least one property of the dark energy, which if we detected that it changes along history, then we say it's not a cosmological constant and maybe it's really a new particle that we never saw it.
Okay.
And it's there in the universe. So that's going to be very exciting.
I will put it in my calendar and then we have to talk again.
Yes,
Because
yes,
it will
about
be,
this.
yeah. Well, you know, I think I come from a place in the world where it's easy to see and go and check your problems. Yeah. And the problem with the universe is it's so big and it takes so long time to get there, to check things.
That's
So
right.
you're every satellite you can get up and out there, I think it's important.
Yeah. Thank
Yeah.
you. Thank
Yeah.
you very much. It's nice to know that you as a taxpayer you agreed to.
Well, I think
pay
this
the
is
taxes for
the right way to use the money, because I think figuring out how the universe works will help all of humanity.
Yes.
I think it's going to be the problems that you solve will have an impact on everyone. You can see Einstein have had an impact on everyone.
Huge. That's
Yeah.
true.
So if we can adjust this, evolve it, I think as long as we use it for the good, of course,
Yes.
it will be a huge improvement.
Yes.
Yeah. So
I agree, yeah.
yeah. Okay.
Thank you for that.
What are the hottest new theories out there now that evolves Einstein's theories?
So nowadays, in fact, we are in a period where people wrote down lots of theories, and now we are waiting for this data to come, in fact. Data from new gravitational waves experiments. So there's going to be one very famous one that's going to be launched in 2027, 2028 called LISA.
Yeah.
So these are going to be 3 satellites where instead of these mirrors to be buried on Earth, there are going to be 3 satellites with lasers in between them.
Yeah.
So each satellite, they are a distance larger than the Earth to the Moon. So it's several millions of kilometers. They have lasers, and you have to have the laser in between them. So it's huge distance.
Yeah.
But then you can imagine that since they're in space, they are much more precise. Any gravitational wave that goes through the lasers, they will create an oscillation which will be easier to measure.
Yeah, because the farther they are apart, the easier it will be, and the more accurate you can be.
Precisely.
Yeah.
Yes, yes. And on Earth, you know, there are earthquakes, there are people driving through, there are lots of things going on. So people need to be very careful when they do these experiments on Earth, while in space, the environment is much more controlled. So with LISA, we will be able to detect many more mergers of black holes. And also with this satellite that I told you, Euclid will come up next year with data, the first data. So hopefully we will see whether there is an evolving dark energy in our universe or if it is just a cosmological constant. That is going to be something very important. And that will rule out many different kinds of theories of gravity. Because there are theories of gravity, as I said, that they imply the existence of new carriers, but other theories of gravity come from the existence of extra dimensions. So our universe is not just 3 spatial dimensions plus 1 time dimension, but maybe we live in 11 dimensions. For instance, people who do work on string theory, they say that the universe is 11 dimensions. And if that's the case, you usually modify also general relativity. Because you can imagine for general relativity is a mathematical description of a 4-dimensional universe. Now you need a mathematical description of an 11-dimensional universe.
Yeah.
Those 11 dimensions, 6 of them, we don't see them. Yes, so they must be hidden. They must be very small, for instance. And this makes modifications to general relativity as well. So people hope that gravitational waves, these new satellites, they will be able to either rule out these extra dimensions, for instance, or maybe give hints, smoking guns, that they exist.
Yeah.
So usually, yes. So I think we are in a period in cosmology that, in fact, we are really waiting for the data to come.
Okay.
More than more crazy ideas, because I think there are already too many ideas.
Crazy.
Yes, crazy, which is necessary. Yes.
Yeah.
Science, you need to go a bit wild.
Yeah.
Within the scientific language, of course, and within boundaries, science boundaries. But you need to go a bit crazy. But now it's time to get data to tell you this theory is correct or this theory is wrong. Yes.
Yeah. Because we also talked about Einstein's theories. It took 70 years also just to verify
Precisely.
gravitas.
Yes. To test, yes.
Yeah.
And you always have to keep pushing the boundaries, yes.
Yeah.
Because, as I said, in fact, we can never verify a theory. You can only somehow, yes, I didn't rule it out.
No.
So you can only measure the gravitational waves I've seen, they agree with Einstein theory of gravity. The movement of planets in the solar system, they agree with Einstein general relativity. The GPS that we use in our Google Maps or whatever, they work so well. Yeah, you managed to come here, probably maybe using Google Maps. Use the GPS or use general relativity. So everything indicates that general relativity is correct, but you need to push the boundaries always, because, as I said, there are also indications that general relativity is not the final answer for how we describe space and time.
Yeah, because in the general relativity, there is also dimensions.
Yes, there are 4 dimensions.
4 dimensions.
Yes.
And, okay, that's only the 4, not 11.
Yes, in general relativity, you have only 3 spatial dimensions and 1 time dimension.
Okay.
If you go, yes, okay. So if you, there are different ways of doing gravity, as I said. If you follow the path of general relativity, you just keep 4 dimensions. And for instance, you add a massive graviton. You have a massive particle, which we know it doesn't work, but you can add that one. Or you can add other particles. So that's one way of studying gravity. Having a mass, adding another particle, etc. The other way of studying gravity is to say, no, gravity should emerge from quantum mechanics as well.
Okay.
And then you go to the path where you try to say, there are no particles. Particles are not the fundamental objects in the universe, like electrons or photons or neutrinos. What we have are strings, and that comes the string theory.
Yeah.
Yes?
Has that actually lost some momentum, the string theory?
It has lost a lot of momentum, in fact. It's true.
I was trying to be polite.
Yes. In the 80s, there was a lot of momentum on string theory. Lots of people, there was lots of funding, lots of people thought it was really promising. And it's a fantastic theory. It's a really nice way of upgrading our standard model of particle physics. But the problem of string theory is that it leads to too many predictions, which a theory is a good theory if you can rule it out. If you can say, I'm going to do this experiment and I can rule out your theory. If your theory is very good, it explains everything, then if it explains everything, then you are like...
Sounds too good to be true.
Yeah, it's a bit good to be true. But on the other hand, it becomes very complex. String theory has too many variables. Now you have 11 dimensions. Okay. And then you tell, well, why 11 dimensional? I only see 3 or 4. Oh, it's because they're very small. Okay, that's kind of an excuse now. Okay, but it's true, if you make them very small, I can't see it. And then you ask, oh, but string theory predicts there are more particles than the ones that we see in the Large Hadron Collider. Okay, where are they? Oh, they are so energetic that you can't create them in the Large Hadron Collider. Okay, that's another excuse. So if you start to give too many excuses,
Yeah, it falls a little bit apart.
yes, it falls a bit apart.
Yeah.
And I think that's a problem with string theory, that it can explain everything, but then you need to hide the extra dimensions, you need to hide the extra particles. And in science, we like a minimalistic model somehow. You know, let's set up a minimalistic structure in order to explain our universe. Otherwise, if you start each phenomena as a different law, it's a bit too...
Yeah, when you talk about multi-dimensions, and it becomes really abstract also. It's really hard to comprehend, and it's hard to explain to people.
Yes, I guess so. Yes,
Yeah.
Even for me, because we are used to that language. Because you do mathematics, and in mathematics, you can always add dimensions to your numbers, etc. So,
What is a dimension in numbers?
no, you can have, for instance, instead of having you have a number, for
Yeah.
instance, is number 1, and then you can have, for instance, in 2 dimensions, you can have a vector.
Yeah.
For instance, you can have vectors with 3 dimensions. So a vector which has 3, you see it in a cube, for
Yeah.
instance.
Okay, now I understand.
And then you
Okay.
can just keep 4,
Yeah, you could
5,
just
10,
add. Yeah.
infinite dimensions. So then that will be a dimensions in.
Okay. Okay, now I understand.
Yes.
Yeah.
But the string theorists, they're talking about spatial dimensions. So they're not just making up some numbers. It's a real thing.
Yeah.
And that's what makes a bit more hard to understand.
Yeah. But it makes a lot of good movies.
It-
Interstellar was a good movie.
Interstellar was a very good movie.
Yeah.
Yes.
Or is a good movie.
Yes.
Yeah, I think so.
And the science is very good there. I
Yeah.
think it was well made. Yes.
Yeah, I liked when they're talking about gravity and the sound that uses that makes it's hours or it's days when they're on this big planet.
On the yes, each because time passes very slow when you are in a very massive object.
Yeah.
So like a black hole or a big planet or a star, time goes very slow with
Yeah.
respect to Earth. Yes.
Yeah. Oh, the sound effects in that movie is amazing.
Yes.
Yeah. Is there anything that you feel that we haven't discussed that we really need to discuss? There is, of course, anti-gravity. When will we be able to just fly away?
Yes, that's the anti-gravity one. If we could control dark energy, because dark energy is kind of an anti-gravity phenomenon. Yes, while
Yeah.
all the rest of the matter in the universe comes together and cluster gravitationally, so there's an enforced attraction. Dark energy leads to some kind of a repulsion. We cannot call it like anti-gravity. There's no point going to the technical details, but it leads to some kind of a repulsive kind of effect.
Yeah.
And if we could one day master and control dark energy into scales where we could create some kind of negative pressure that would make us move apart from each other, then we could very easily evade the Earth and send rockets to different places. But I think it takes it will take I think a few hundred years or thousands of years until we get to that technology.
I would just like to, what has SpaceX made possible with their expansion of sending satellites to the moon? No, not to the moon, the satellites into space.
Yes, well, so this Euclid satellite was sent by SpaceX.
It was, yeah.
And the reason was because the satellite was supposed to be sent by Russia. And there was the problem with Ukraine, so Russia was out of the...
Out of the question.
Out of the question. We contacted Ariane, the French space agency, but they couldn't send it. So we end up
With SpaceX.
sending SpaceX.
Yeah.
So, and nowadays I think it's playing a quite important role in sending satellites. Maybe not very big satellites, but small satellites can be sent by SpaceX. So it's...
Yeah, they
It's,
at least have a pretty clear vision that they want to make us interplanetary.
Yes, yes, and I think it's fantastic to tell
Yeah.
the truth. I think it's fantastic that
Of course, yeah.
we try to leave Earth. It's like, as I say, we only know a little bit of our universe. It's like,
Yeah, I think we have to go there.
yes,
Yeah,
we have to go there.
Yeah.
I think we have to go, and for that it means investing in technology, investing in science, and making maybe less wars because they're so expensive. It's like a waste of resources and.
Yeah, I think
Yes, which is a
wars
pity.
is kind of the last thing that we actually should.
Should be doing.
Yeah.
Yes.
Yeah, I think there should be compromises along the way that could end things. But who am I?
Yes,
Yeah.
yes, where we, yes, unfortunately.
Okay, I think this is a really good place to wrap up. Thank you so much for your knowledge and your time. It's been a blast, and we need to talk again when the new data comes next year.
Yes, absolutely. No, thank you very much. It was my pleasure being here. Thanks for this opportunity. And yes, I'll be looking forward in March next year. Contact me and then I'll let you know something about dark energy, hopefully.
Can't wait. Thank you so much.
Thank you.
Thank you, David Mota, for this conversation. The further we look into the dark, the more light we find. Black holes, dark energy, even time itself is still unknown, still calling for us to understand. Maybe Euclid will bring us some answers, maybe it will bring us new questions. Either way, the universe is speaking and we are still listening, trying to understand. Catch you in the next one.